So last week we looked at solving systems of equations by graphing, which was a pretty good way, but tough to be accurate sometimes on a graph. So today we're going to look at one of the first ways of solving using algebra. So today we're going to look at solving by substitution. The next lesson is going to be solving by what's called addition, or sometimes it's called elimination. So here's the substitution property. This is the principle that we'll be using if A is equal to B. So one quantity is equal to another, then A can be replaced with B in expressions and equations. Now I just made this note here because A doesn't always just represent a single variable. A could be 3x plus 9, or A could be 50 minus 2y. Like 50 minus 2y equals B. So it's not always just a number or a single variable, it could be an expression. And that's the concept we're going to use to solve systems of equations by substitution. So let's just jump right in and get started here. Substitution, there is a kind of a list of the steps there on your paper that kind of walks you through it. The idea is first you want to solve for one of the variables. There's four places where variables show up here. We want to solve for one of these. Now all of these are pretty simple because all of their coefficients are 1. There's a 1 in front of each of these. This is a -1, but still a 1. And we want to solve for one of those. So in this one, we could choose any of the four, and they would all be pretty simple. Other times, there will be a specific one that's going to be easiest, and the easiest one, again, is one that has a coefficient of 1. If it had a 3 here, and you were solving for this, you would end up having to divide by 3 and have fractions. So let's go ahead. Let's just solve for this x right here. So we have x plus y equals -4. We're going to subtract y from both sides, which leaves us with x equals -y minus 4. And the idea of substitution is now that we know what x is equal to this expression, we can substitute this part in for x into another equation. So we do not want to substitute it back into the equation we just worked with. That will get us nowhere. We'll end up with -4 equals -4, and that's not very helpful. So once you solve for one of the variables, you plug that in to the other equation. So what we're going to do here is we're going to take our -y minus 4 and put it in for x. So instead of having x, we're going to put -y minus 4, still minus y, equals 10. Now in this case, we don't really end up needing the parentheses. Sometimes it's going to be important because there might be a negative out here and that would get distributed. That's why I put it there, just to remind you to put the parentheses there. But again, in this case, we can't simplify this. There's nothing outside to be multiplied in here. So really this is just the same as -y minus 4 minus y equals 10. Now we want to solve this. We want to solve for y. So we have a -y and a minus y, which gives us -2y. Minus 4 equals -10. Add 4 to both sides. And you get -2y equals -10 plus 4 is -6. Divide both sides by -2. And you get y equals 3. Now we're solving a system of equations. So once you get here, sometimes we think, oh, we worked through all that, we got y equals 3, we're finished. We need to solve for the system, which means when we think of in terms of graphs, we want to find the point that we could plug in to both of these that would make these true. So we need to find a point. So now what we're going to do, I think our book calls it back substitution. We're going to take our y equals 3 and we're going to put it back into this equation here. Now you could put it into one of these two. This one's set up nicer because we can just plug it in. So we take that equation there, x equals, and it's negative y, well y is 3, minus 4. Negative 3 minus 4 is 7. So we got x equals 7, y equals 3. So our point is 3, I'm sorry, I forgot the negative there, 3 negative 7. Now let's check if our answer works. Taking our point, x is 3, y is negative 7, put it back in here, this would be 3 plus negative 7 does equal negative 4. Putting our point back into this one, 3 minus negative 7, well, it's the same as 3 plus 7 equals 10. So 3 negative 7 works. Moving on to our next example here, x plus y equals 5 and 3x plus 7, or 3x plus y equals 7. Here we have 4 variables here represented. We could solve for this x or this y or this x or this y. Now looking at this one and thinking about what I said last time, you should realize there is one that's not necessarily a good choice. It still would work, but it would make it harder. So we do not want to solve for this x here because we would end up having a fraction with a 3 in the denominator. So let's go ahead and solve for this y here. So we have x plus y equals 5. We'll subtract x from both sides. And we get y equals 5 minus x. We can go ahead now and take this, y equals 5 minus x, and substitute it in here. So we have 3x plus y, and y in this case is 5 minus x, equals 7. Put the parentheses here. You should do that as habit, and then in this case it ends up we didn't really need them. So we have 3x plus 5 minus x equals 7. 3x minus x is 2x. Plus 5 equals 7. Subtract 5 from both sides. 2x equals 2. Divide both sides by 2, and you get x equals 1. Now we're going to use that idea that back substitution. We found x is equal to 1. We're going to go ahead and plug it back into this one right here. That's the one that makes the most sense and will be easiest to figure out. So we're going to come back. We're going to do y equals 5 minus x, which in this case we found x is 1, so y equals 4. So our solution here we got is 1, 4. Now how do we check that? Well, we want to put it back into both to make sure it works for both of them. Always check both because it could work for one and not for the other. So putting in here, 1 plus 4 is 5, that works. 3 times 1, because we're putting x in for, or 1 in for x, 3 times 1 is 3. Plus y, which was 4. 3 plus 4 is 7, so it does work. So the solution to this system is 1, 4. Now, just thinking about that graphically, these two lines would intersect at the point 1, 4. I mentioned a couple of terms last time. This would be a consistent, independent system. Consistent because it has a solution, and independent because there's just one solution. If there was no solutions, which might as well tell you this now, if you work through a problem, you do your work here, and you end up with something that's false, if you ended up with something like 7 equals negative 3, that would indicate that there's no solution, which means the lines would be parallel. So if you work through something here, get something that's false, one number that's equal to another number, and it's not really true, that means your system is inconsistent. Another thing, if you work through here, you do everything right, and you get something that is always true, such as 3 equals 3, or -7 equals -7. If you come to something that's always true, that means you have a consistent dependent solution, which means the two lines or the two equations that you started with would have been the same, would be representing the same line. So that goes back to what we talked about the other day about consistent dependent, consistent independent, and inconsistent. So in this case, we got an answer, we got a solution, so that's consistent and independent. Coming to our last example here, I did skip an example, I think, so this is the last one. And I'm doing this one really to show you that it is helpful to have another way to solve these systems, because our substitution method will work here, but it won't be look the best. It won't be the best way to do it. So we want to substitute. So we want to choose to solve for one of these variables. Now in this case, none of the coefficients are 1. So there's not one that there to solve for that's really easy. I would the next easiest, I would go with this one, because 2 usually isn't too bad to work with. So I'm going to take this equation here, and I'm going to solve that for x. So I'm going to subtract 3y from both sides. 2x equals 16 minus 3y, and divide both sides by 2. So I get x equals 16 minus 3y over 2, which again doesn't look that easy to work with. I think it's going to work out okay here, but so now that we have this, remember what we're going to do is we're going to take x, we solved and found x was equal to this, and we're going to put it in for this x right here. You put it into the x into the other equation. So we're going to have 4 times x, which we found was 16 minus 3y over 2 plus 5y equals 28. This works out kind of nicely here. 4 times this is going to cancel with this, become 2. Now we'll distribute. So we'll have 32 minus 6y plus 5y equals 28. We can add these like terms. 32 minus y equals 28. I'm going to subtract 32 from both sides. Negative y equals -4, multiplying both sides by -1. Negative y equals -4, then positive y equals +4. We're not finished. We found what y is. Now we're going to plug that back into this one. I'm going to come up to the top here now, or maybe midway. X equals 16 minus 3 times, we found y was 4, over 2. 16 minus 3 times 4 is 12, so 16 minus 12 is 4. 4 over 2 is 2. So we came up with the solution. X is 2, y is 4. Plugging that back in, 2 times 2 is 4. 4 times 3 is 12. Which 4 plus 12 is 16. Putting in this one, 4 times 2 is 8. 8 times y, which was 4, is 20. 8 plus 20 does equal 28. So our solution is correct. So that's the substitution method. It's more precise than the graphing method, because sometimes on our graph, if our spacing was off, our lines or points were a little bit off, we might not have gotten to a nice easy solution like this. So using algebra really can take away from that inaccuracy. All right, you can use the rest of this time to work on your homework.